field-assisted sintering of advanced ceramic materials on Nickel. This is Seth and Alejandro, and our advisor, Fred Chang. So we will, over the course of this presentation, we will be covering our problem statement, which includes our project description, motivation, and goals, our literature survey, which covers sintering, driving force, sintering types, and field-assisted sintering. We'll see flash sintering mechanism, how it works, and what Joule heating, how Joule heating affects it, the related standards, our challenges, the global design components, our die design, and our die design alternatives. You'll see our proposed system, our timeline for the year, and our proposed work at the end. So for our problem, we want to build and design a flash sintering machine. We want to successfully sinter ceramic materials, and at the same time record that sample's temperature in real time, and then afterwards test the sample's mechanical properties. We hope to control undesired reactions to high temperatures, reduce harmful and unwanted waste, and investigate flash sintering mechanisms. Sintering occurs when interparticle pores in granule materials are eliminated by atomic diffusion. When you lower the freeze energy in a system, sintering happens, and some of the driving forces are the curvature of the particle surfaces, an externally applied pressure, or a chemical reaction. There's several methods to sinter that exist right now. One is applying the pressure to a sample, which can take hours. Hot pressing, which is applying pressure and applying heat at the same time, and the heat temperatures rise to over 2,000 degrees Celsius, which also takes a considerable amount of time. Microwave sintering, which uses radiation to superheat material. It's faster, but it still takes some time. And finally, field-assisted sintering, which can hopefully take seconds.
So I'm going to talk a little bit about what field-assisted sintering is. As we mentioned in the previous slides, we also talked about flash sintering. Flash sintering is a sub-component of field-assisted sintering. In field-assisted sintering, we use an electric current passing directly through the sample instead of pressing it with pressure. So this electric current passes directly through the sample, and it heats up the sample from the inside out, causing it to densify in less time and at lower temperatures than conventional sintering. In flash sintering, reports have shown that sintering actually could occur at less than 5 seconds, and it could occur at temperatures as low as 800 degrees Celsius compared to the 1,000 and something degrees Celsius that conventional sintering shows. One of the explanations for field-assisted sintering and flash sintering is the Joule heating effect. This is caused by the electric current passing directly through the sample, and like I said, causes the sample to heat up from the inside out. This is one of the equations that is proposed to explain this phenomenon, and one of the equations that we will be using in our design process to show some hand calculations and compare them with the results at the end. It assumes that we use a power supply, and you have the temperature of the furnace, and you also use the surface area of the sample, and you can calculate the change in temperature of that sample using that equation. As well, you can also use this other equation, which it's based on the volumetric thermal expansion of the sample. As the sample heats up, the volume of the sample increases, and using that, you can also calculate the change in temperature. For the standards that we are going to be working with, we have chosen to use the International Organization of Standardization. It is a well-known organization throughout the world, and it has published many papers. And mostly we're going to be focusing on the ceramic part of these standards, on how to choose the right ceramic, how to find the ceramic properties, how to find the material properties, how to find the thermal properties, and all those related properties that are very important for choosing the right material for this process. These are some of the examples of the standards that we will be using. Not all of them, we have many more. And now, we're going to talk about the challenges.
All right, well, my name is Seth. I'll be discussing the team's challenges, our global design components, and our initial design. The main challenge for us is to successfully flash center a material with one of the furnaces that's in the nanofabrication lab. We have a furnace that can reach 2,700 degrees, but as my partner said, flash sintering, the objective is to reach sintering at a lower time and a lower temperature. So that would be our main objective. Also, during the literature survey, we found that other teams have successfully densified material to 90%. We aim to reach 90% and then reach a little higher, 95, 98%. I spoke with Dr. Bates and he said if we do successfully flash sinter material, he can provide the mechanical testing for us. All right, for global design components, piggybacking off the last one, there are other teams that have successfully produced flash sinter material. So we feel that we can actually contact them to discuss design specifications, roadblocks, and results. And our initial purchase for the power supply was from Germany. So we felt that we had to convert the euros to US dollars. However, we did find a domestic vendor to provide a power supply, so that we don't need anymore. All right, for flash sintering, we can't just put the powder inside of the furnace. We have to press the powder so that we can connect it to the power supply. Here you have the conventional die that's used to press the powder, and in the middle, the press used to apply the pressure. Next. However, during literature survey, we found that a dog bone-shaped die will allow for more even current distribution. We initially thought that a rectangular die would be less complex to manufacture in-house. However, we will consult Mrs. Ickrelli in the student shop to confirm this or rebut this. Here you see on the left and on the right depictions of top views of the sample within the furnace during sintering, and in the middle the sample that's in the die used to press it. Next. Here is our timeline. Up until now, we've been conducting literature survey, initial design, initial design specifications, and material component selection. We've already purchased the power supply, so next will be the material purchase, and next the metal wires to connect the power supply to the sample. So we will perform tests on the die because we are designing it ourselves. We have to make sure it will withstand 12 megapascals of pressure, because that's what we've seen to press the powder in other literature survey. And thank you. This is our presentation.
Have you calculated how many the voltage and current required to
Yep.
simple?
So for the power supply that we selected, the range goes from 0 to 100 volts, from 0 to 15 amps, and the maximum power output is 1.5 kilowatts. So with that range, we are aiming to play around with the voltage and to see which one gives us the best results. But we already selected the power supply, and that's already done. It's based on the literature survey of what we've seen other experiments have worked with.
One challenge for our team is we can't look into the furnace to see if it has sensor, so we do plan on purchasing thermocouples. It says to record temperature in real time. We've seen during flash sintering that when flash sintering occurs, there's a spike in temperature. So we plan to use that to record the temperature in real time and use a data acquisition system.
Quick question. If I understood correctly, you said that you're planning, your ideas have the ceramic material embedded some kind of electrical current to make it work.
Intensify.
Once the ceramic is formed, does that electrical piece that goes in the system stay in the ceramic, does that stay with the ceramic or are you going to remove it?
No, like, I mean, we're trying to use probably platinum wires to be around the ceramic.
Oh, okay.
Connect it with like a platinum paste, just
That's
attach it
it.
on the sides.
Passing the current to the ceramic, and then after the ceramic is identified, we can remove the sample.
Okay, because that's where I was confused. It was embedded inside the ceramic and I was like,
No, it's not even inside.
how are you going to take it out?
It's using the ceramic. Most likely we'll be using platinum paste to
Okay.
connect it around the ceramic surface.
Okay.
And that's going to pass the electric current, and then once it's densified and solid, we can remove it and put it properly so that.
Okay, yeah, that was my confusion. How you get okay.
Have you put that? Oh, sorry.
No, I'm done.
How do you protect the compression machine from the electrical current?
No, the die won't be inside the
Oh,
furnace.
he won't be there, okay.
We're just using that to press the powder.
Oh, it's just basically
Yes, the powder
clamping
is-
it, if you will, and then,
The
okay.
powder needs to have a certain compression, and we will be doing
Got
that
it.
separately
Got it.
before putting in the type furnace.
Okay, so this is a general, just a comment about the presentation. What you're talking about here is occurring on a very small scale. It's difficult to visualize. I think you could benefit from some diagrams or some basic visuals of what's going on. You talk about densification. To show how that's occurring, especially when you start talking at the molecular level, that you're removing gaps and it's very simple diagrams. I think that could benefit that.
Any more questions?
Mr. Nyman, you were going to say something?
No.
You were? Well, thank you very much.